Light gathering and resolution. The most important of all the powers of an optical telescope is its light gathering power. This capacity is strictly a function of the diameter of the clear objective, that is, the aperture of the telescope. Comparisons of different sized apertures for their light gathering power are calculated by the ratio of their diameters squared. For example, a 25 cm, 10-inch objective will collect 4 times the light of a 12.5 cm, 5-inch objective. 25 times 25 divided by 12.5 times 12.5 equals 4. The advantage of collecting more light with a larger aperture telescope is that one can observe fainter stars, nebulae, and very distant galaxies. Resolving power is another important feature of a telescope. This is the ability of the instrument to distinguish clearly between 2 points whose angular separation is less than the smallest angle that the observer's eye can resolve. The resolving power of a telescope can be calculated by the following formula: resolving power equals 11.25 seconds of arc/d, where d is the diameter of the objective expressed in centimeters. Thus, a 25 cm diameter objective has a theoretical resolution of 0.45 second of arc, and a 250 cm, 100-inch, telescope has one of 0.045 second of arc. An important application of resolving power is in the observation of visual binary stars. There, one star is routinely observed as it revolves around a second star. Many observatories conduct extensive visual binary observing programs and publish catalogs of their observational results. One of the major contributors in this field is the United States Naval Observatory in Washington, D.C. Most refractors currently in use at observatories have equatorial mountings. The mounting describes the orientation of the physical bearings and structure that permits a telescope to be pointed at a celestial object for viewing. In the equatorial mounting, the polar axis of the telescope is constructed parallel to Earth's axis. The polar axis supports the declination axis of the instrument. Declination is measured on the celestial sky north or south from the celestial equator. The declination axis makes it possible for the telescope to be pointed at various declination angles as the instrument is rotated about the polar axis with respect to right ascension. Right ascension is measured along the celestial equator from the vernal equinox, i.e., the position on the celestial sphere where the Sun crosses the celestial equator from south to north on the first day of spring. Declination and right ascension are the two coordinates that define a celestial object on the celestial sphere. Declination is analogous to latitude, and right ascension is analogous to longitude. Graduated dials are mounted on the axis to permit the observer to point the telescope precisely. To track an object, the telescope's polar axis is driven smoothly by an electric motor at a sidereal rate, namely, at a rate equal to the rate of rotation of Earth with respect to the stars. Thus, one can track or observe with a telescope for long periods of time if the sidereal rate of the motor is very accurate. High-accuracy motor-driven systems have become readily available with the rapid advancement of quartz clock technology. Most major observatories now rely on either quartz or atomic clocks to provide accurate sidereal time for observations as well as to drive telescopes at an extremely uniform rate. A notable example of a refracting telescope is the 66 cm, 26-inch, refractor of the U.S. Naval Observatory. This instrument was used by the astronomer Asaph Hall to discover the two moons of Mars, Phobos, and Deimos, in 1877. Today, the telescope is used primarily for observing binary stars. The 91 cm, 36-inch, refractor at Lick Observatory on Mount Hamilton, California, U.S., is the largest refracting system currently in operation. The 1 40-inch instrument at Yerkes Observatory in Williams Bay, Wisconsin, U.S., has been inactive since 2018. See table.